The example of the pendulum that we've just seen comes from the mathematical domain, the mechanical domain, beg your pardon. And in the mechanical domain, things unfold very predictably, and the notion of a mechanism that is a bunch of interacting parts that collaboratively achieve some goal has been of profound influence in our scientific theorizing. But the mechanical universe perhaps exerts too strong a pull on our imagination. And it's notable that very many scientific papers at present tend to open with a statement. They set up their problem something like this: humans do this, that, and the other. The mechanism by which this is achieved is not known. And they proceed to carry on their inquiry as if mechanism were the be-all and end-all of scientific description. It absolutely isn't. We need to be cautious here and to realize that a mechanical description is a specific form of description, and it will not answer all the questions that we have. It would be helpful at this juncture just to clear up a little bit of terminological confusion. As I said, the field of dynamics is so pervasive in science that there are several notation systems around, and these are illustrated there on the right hand side of the slide. I see I have a typo in the slide. It should say x is a function of time, x equals ft. We can, of course, generalize our descriptions to one thing as a function of any other thing, but in dynamical systems we're usually interested in x, the state of the system, as a function of time. The first derivative of that we've met already. This is the instantaneous rate of change. And we've used the notation dx dt. It's a convoluted notation. It has a long history. But there are other ways to write the exact same thing. So x with a little dot over it, pronounced x dot, means exactly the same thing. And if we describe x as a function of time, f of t, then f prime x is also the first derivative, or the rate of change of that function. And that is, of course, itself a function. And we could take the rate of change of that function itself, and then we get acceleration. That's written in the dx dt notation with this dreadful, misleading kind of script where we get d2x dt, d squared x dt squared. That's not squaring in the normal sense. It means the second derivative. It's much more concisely expressed as x double dot, or as f double prime of x. So, in a mechanical framework, the relevant features of the components within the system are described by two numbers per component, the position and the velocity. We just saw this in our description of the pendulum. And in the mechanical domain, and only in the mechanical domain, there is a necessary linkage between position and velocity. The two together serve to pick out one massive body moving within the system. The second law of motion of Newton says that force is mass times acceleration. Acceleration is that x double dot, which is some function of the state of the system, that is x and x dot, and the function indeed is given by f equals ma. So there's our state, and there's our dynamic. Those are the two elements that we need when we're doing a billiard ball kind of description. That is true and invariant in the domain of mechanics. But the description of lawful change of state over time extends far beyond mechanics, and in most domains, and for most systems, we will not have available to us something as handy as Newton's second law of motion. That is, we will not typically have available to us an explicit dynamic. We may choose to suggest certain possible dynamics, but we will not typically have an analytic form that we can write out like that. Nevertheless, the suite of concepts that are curated here under dynamical systems theory are very, very rich, and they continue to be of use in describing highly complex systems and their interactions, even in the absence of an explicit term that describes the dynamic. And in our inquiry, we will be interested not only in continuous dynamical systems, but also in discrete dynamical systems, as found, for example, in a recurrent neural network. In a discrete dynamical system, we have the same pairing of state and dynamic. The state simply is all the numbers needed to describe the system at time t, and the dynamic is the update rule of a network. It's the rule that generates the state at time t plus 1 as a function of the state at time t plus inputs, parameters, and so on. In what follows, we will mostly be describing continuous dynamical systems, but discrete dynamical systems will provide us with some useful examples, not least in our exploration of chaos in what comes. So, remember the core definitions that we started with. A dynamical system comprises a state description and a rule governing state change over time. And this provides us the tools with which we can, among other things, address the puzzles that arose with Zeno. So many issues in science become tractable when we take this principle sort of approach. Increasingly, dynamical systems vocabulary is used in classical problems to do with human living, we mentioned economics and social sciences, in the psychological sciences and the cognitive sciences. And when we do so, when we adopt this kind of terminology, we are not assuming any psychological constructs. We are not assuming the person is a pre-given system. The system that we pick out may be just a few pieces of the body, so a lot of important work, and some we'll be looking at, looks at the interactions between two fingers wagging. Some of my work has been done in modeling the vocal tract, in which case various parts of the vocal tract are taken as the elements of the system to be characterized. Two hands is not a person. A few selected parts of the body is not a person. Our system might be the whole body, or it might be the body plus a tool. It might be multiple bodies, as here. So the employment of dynamical systems vocabulary is agnostic with respect to any view of the person, the mind, or what behavior is. We don't necessarily know in advance what the system is that we're dealing with. That is something that at the start of our modeling exercise, we delineate. It depends on the phenomenon or behavior being studied, and dynamical systems does not presuppose any existence or essence to that system, psychological or otherwise. And there's an important corollary of this, which is that when people start to use this terminology, they often say, well, is that a dynamical system or is it not a dynamical system? That question makes no sense. Something is not either a dynamical system or not a dynamical system. Characterizing it as a dynamical system is a way of describing it using this terminology. And that may be useful, and it certainly is in the case of the pendulum and so many other of the activities of science, or it may not be. The employment of the sophisticated apparatus of differential equations does not guarantee any sanity. The sanity of the exercises rises in the wisdom of the inquirer, of the researcher who decides this is what we're going to look at and we're going to exclude the other. That's the essence of science. And we're going to wrap up this short video with this quote from Heisenberg of the famous uncertainty principle. He noted that science alters and refashions the object of investigation so that method and object can no longer be separated. This is very, very important. Science is a constructive activity in which we do not simply capture the essence of the world through a luminous glass in which the world is revealed in its entirety. Rather, we employ methods that select objects that partition the flux of the cosmos into the thing we're looking at and everything else which we will hold in abeyance. So if you apply dynamical systems concepts in a wrong way, you can end up in the mud, you can drown. And one thing that's very important to recognize is that our imaginations have been shaped by a lot of developments in science and technology and media. And we tend to think of reality as if reality was something that could be captured in a photograph. And a photograph gives you the sense that you've captured the state of something. But a photograph misses an awful lot of things. The state of something is not necessarily something which has that kind of punctate existence that can be captured by a photograph. So remember, reality is not the kind of thing that can be captured by a photograph. Rather, a photograph, like a dynamical systems inquiry, is a way of framing our inquiry in order to see if we can thereby render something intelligible.